We'll start the class soon. Just wait for 2-3 minutes. Okay, let all the students to come. So, am I audible to everyone? Hello. Am I audible to everyone?
Yes, sir, you are.
And
Yes,
the
sir.
screen is also visible.
Yes, sir.
Screen is also visible. Okay. So let us do the recap of what we have done in the last class, and then we will start. By the time the other students will also join. Okay. So the last class we started looking at the steady state heat conduction cylinder and sphere when there is a heat generation source was there. Okay. So this type of systems are common in process applications, and the commonly used application is the reaction over the catalyst pellet, isn't it? So heat is generated inside. The another example could be a nuclear rod where the bombardment of a neutron may generate the heat inside, correct? And also a day-to-day life example is the electrical wire where the conduction of the electric current generate the heat inside, and this heat is dissipated in a radial direction. So we have seen the steady state heat conduction with heat generation source for a plane wall, and also we have seen for a cylindrical wall, uh, cylindrical wire. So this was a more generalized case where the current was flowing through a wire, metal wire, and outside of the metal wire the electrical insulator was there. So this insulating material will also act as a insulation for the heat coming out uh, from the wire. Okay. Just wait, I'm just coming. Okay, sorry. So this was a generalized case which we have seen for the cylindrical wire. So we have solved the temperature distribution in a metal, and then we have also solved the temperature distribution in a insulating material which is outside of the wire. Okay. Again, in case of the insulating material, there is no generation term, and the generation term is only present for the metal wire. So based on that, how the temperature is going to be distributed in a radial direction, that we have already calculated, and that is given by this equation. And also how the temperature distribution will be there in an insulation material, that also can be obtained by putting constant C3 C4 in equation number 7. This particular equation which I have given for the temperature in the insulation material. This is exactly at the boundary of the metal wall and the insulation. Okay, so this was a more generalized case. You can solve even a simpler case where you can assume that there is no insulation material outside the wire. In that case, you will get a much simpler equation. Similar to this, we have again then moved on to the spherical system where there is a heat generation inside. In this case also we have obtained the temperature distribution across the radial direction, and also we have said that the maximum temperature will be at the center. So that can be obtained directly by putting radius r equals to 0 in this particular distribution equation, and you can get the maximum temperature at the center. So I am not going in the detail of this because anyway we have covered this in the last class. So I am just quickly browsing through whatever we have done in the last class. Okay, so one example is solved based on this. Again, I'm not going to discuss this in detail. That is anyway we have discussed in the last class. Okay, so this is what we have started in the last class barely. So let us look at this particular topic in more detail. Okay, so unsteady state conduction in a rectangular solid. So as I said in the last class, we are keep on adding the complications in our analysis. We started with a planar surface first, then we have moved to a cylindrical and the spherical surface where the heat transfer area was variable. Then we have moved on to another complication where we have said that the heat generation source is there. Doing that further one level up, where we are saying that in addition to the generation, there is also accumulation term is present. Accumulation term is present. Okay, so let us assume that there is a rectangular element as shown here in the figure. Again, the heat input occurs to the again in order to analyze this, since we have action source and also there is a accumulation term, so definitely we need to make a shell balance, and in order to make a shell balance, a rectangular shell which is shown inside this particular rectangular block is shown here, and this rectangular shell is then enlarged in the second figure. Okay, so here in this particular element, the heat input is taking place through the surfaces ABGF, ADEF, and ABCD. And again, the output of the heat takes place from the opposite surfaces of these given surfaces. Okay, so let's look at the individual input terms. So the rate of heat input to the through the surface ABGF is area into heat flux, and that is at the location X. So that becomes delta Y delta Z, that is the area, cross sectional area, into Qx. Qx is nothing but the heat flux at the location X. Okay. Similarly, the heat input through the surface ADEF. So ADEF surface is ADEF. So here you can see the heat input is from this side. So clearly the surface area is going to be delta X delta Z, because that is going to be the cross section. The heat transfer is taking place from left to right direction in this element shown in text figure. So the surface cross-sectional surface area, the cross-sectional area in this case is going to be delta X delta Z multiplied by corresponding heat flux. So heat flux in this case is going to be Qy, which is at the location of Y. Okay. Similarly, the heat input to the surface ABCD. So ABCD surface is this bottom surface. So heat is taking place from bottom to up. So here the surface area is going to be delta Y, delta X, Y delta is going to be the surface area, and corresponding heat flux is going to be Qz at the location Z. And these are three input terms. To these three input terms, there is a output, heat output taking place from the opposite, the opposite surfaces. So the heat coming out from the surface CDEF is delta y delta z qx x plus delta x, because the thickness along the x direction for this element is delta x. So this is at the location x plus delta x. Similarly, the heat output from the surface, heat coming out from the surface BCHG is going to be delta x delta z. That is going to be the area of the surface into a corresponding heat flux Qy, and this is at the location y plus delta y. And also the heat coming out from the surface EFGH. So EFGH in this case is going to be EFGH is nothing but the heat on surface is going to be delta x delta y, the corresponding heat flux QZ at the location z plus delta z. So these are the three input terms and three output terms for the given example. Again, there is a rate of there is a volumetric heat generation taking place uniformly throughout the element. So volumetric rate of heat generation is nothing but psi v, and since we are saying it is a volumetric rate of heat generation, the total rate of heat generation we can obtain by multiplying a volume of this element. So volume of the element in this case is delta x delta y delta z. So the total rate of heat generation in the element becomes delta x delta y delta z into psi v, where psi v is nothing but internal rate of volumetric rate of heat generation. Okay, so this is up to this. Anyway, we have already seen in earlier examples also. The additional term which is coming in this particular case is the accumulation term. So how much heat is accumulated with respect to time, that is calculated here as dou by dou t delta x delta y delta z rho cpt. So this is nothing but the accumulation term. So now we know what is the input term, what is the output term, what is the accumulation term, what is the generation term, and now we can make a heat balance for a given shell. Okay, so let us look at the heat balance in the next slide. Okay, now so the heat balance here, you can see the input terms are first added, then subtracted by the output terms. Then the generation term is again input, and this entire summation is going to be equals to the accumulation term. So that becomes dou by dou t delta x delta y delta z rho cpt. So basically it is input minus output plus generation equals to accumulation. So that is the heat balance equation that is the balance equation we use for making the balance for mass as well as heat, isn't it? Okay, so now in this particular equation which is at the top, uh, delta x delta y delta z. So if you divide this entire equation by delta x delta y delta z and rearrange the term, by rearranging the term what we are going to get is qx at x minus qx at x plus delta x divided by delta x term will be there, plus qy at y minus qy at y plus delta y divided by delta y. Similarly, the last term is going to be qz at z minus qz at z plus delta z divided by delta z is going to be there. Plus we are going to have and the right we are going to have rho cp dou t by dou t. And since the equation qx at x minus qx at x plus delta x divided by delta x, this is going to be this difference equation can be represented in a differential form. So this particular difference equation can be written as minus dou by dou x qx. So by doing that, all these rearrangement, what we finally get from heat balance equation is nothing but minus dou qx by dx minus dou qy by dy minus dou qz by dz plus iv equals to rho cp dou T by, okay. So this is the equation number one. Equation number one, we are going to get it when we do the heat balance for all the input and output terms. Okay. Is it clear to everyone so far? Okay. Now we can replace the flux terms Qx, Qy and Qz using Fourier's law of conduction. So Fourier's law of heat conduction says Qx is going to be minus K dou T by dou X. And Qy is going to be minus K dou T by dou Y, and similarly Qz is going to be minus K dou T by dou Z. Here you can see, instead of using the normal differentiation, we are using it because these are varying along the x, y and z independently. Okay. So by putting this Fourier's law of heat conduction in equation number one, then we get a double partial differentiation, so that after simplifying what we get is k dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square plus psi V equals to rho Cp dou T by dou T. So here you can see what we are assuming in this particular equation is thermal conductivity. We are assuming that is a constant and is not changing along the coordinate axis. Also, we are assuming that the density and specific heat are constant and these are not changing with temperature. So thermal conductivity, rho and Cp are not changing with the temperature. These are the assumptions we are making here. So based on these assumptions, we are getting a simplified equation as shown here, where the final equation obtained is K in the bracket dou square T by dou X square plus dou square T by dou Y square by dou Z square, and outside of the bracket plus psi V equals to rho Cp dou T by dou T. Here the numerator is corresponding to the temperature, whereas the denominator is corresponding to the time. Okay. So anyway, is it visible? The slides are visible?
Yes, sir, the slides are visible, just your voice is breaking in between.
My voice is breaking in between. That could be because of internet connectivity. Am I audible now?
Yes, sir, it's much better now.
Please stop me if I'm not audible anywhere. Please stop me in between. Okay. Because
Sure.
I am directly on the slide, so I don't get to know whether the connectivity is okay or not. Otherwise, that message pops up in the team. The connectivity is not good, but I am directly on this PowerPoint presentation, so I don't get to see that screen, another screen. Okay.
Yes, sir. Got it.
So please stop me in between if I'm not audible. If my slides are not visible, please stop me in between, and then we can correct the problem. Okay.
Yes.
So by rearranging the term, what we get is 1 by alpha dou T by dou T, and that is equals to dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square plus psi V by K. So here alpha is nothing but the thermal diffusivity. Thermal diffusivity is defined as rho Cp. So this is equivalent to the actual diffusivity which we see in the mass transfer, or the momentum diffusivity which we see in the momentum transfer. So this is similar to that. Okay. So again, this bracket term involving the second derivative can be represented by del operator. So del square we can write down for this entire bracket term, which is of dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square. So this entire bracket involving these three terms along three different axes can be replaced by another operator, which is nothing but del square, and this del square we have replaced in this equation. So what we get is 1 by alpha dou T by dou T plus psi V by K. So this is the final equation. Again, Again, if this particular final expression we can further simplify if we are assuming that no heat generation term, if there is no accumulation term, in that case what we get is del square T equals to 0. So this is a famous Laplace equation which is regularly used by people. Okay, so del square T equals to 0 is a Laplace equation, and we get Laplace equation when we are having no generation and no accumulation term. So basically the Laplace equation is going to give me the distribution of the temperature in different axes, isn't it? So if there is a heat conduction taking place from X, Y and Z, all three phases, in that case we can use a Laplace equation del square T equals to 0. Okay, if there is no generation and accumulation term. So these are the final equations for the unsteady state conduction in a rectangular solid. So let us extend this for a cylindrical surfaces. So let us do the analysis for the cylindrical surfaces. Similar to what we have seen for the rectangular surface. Again, in this case, in addition to the generation term, in addition to the accumulation term, the heat transfer area along the radial direction is going to vary. A similar analysis we have already seen previously, so we will extend this particular analysis further with the accumulation term. So rate of here, in order to make the heat balance in a cylindrical surface, a cylindrical shell is assumed at a distance of r from the center. Again, the thickness of the cylindrical shell is delta r. So the heat is coming in or going out from the radial surface here. So rate of radial heat input through the curved surface at r is given as the radial surface area 2 pi r delta r into the heat flux at r, so that is QR at r. Similarly, the rate of axial heat input through the annular surface, whatever the heat input taking place in an annular surface along the z direction, that can be obtained as 2 pi r. So that is going to be the circumference of this cylindrical shell, and into the thickness of this shell is delta r. So that becomes 2 pi r delta r QZ at the location Z. So this location here is nothing but Z, and the thickness of the cylindrical shell along the axial direction is delta Z. Okay. Similarly, the rate of radial heat output from the curved surface at r plus delta r is going to be 2 pi r delta Z QR at r plus delta r, and also the rate of axial heat output through the annular circular surface at Z plus delta Z, which is nothing but right hand side of this cylindrical shell. So that is going to be 2 pi r into delta r QZ Z plus delta Z. Okay. So these are the input and output terms in a radial direction as well as in a axial direction. Okay. So again, in a similar case to what we have seen earlier, the rate of heat generation in this case is going to be again the volumetric rate of heat generation multiplied by volume of this cylindrical shell or element. So the total rate of heat generation is going to be the volume into the volumetric rate of heat generation. So this becomes 2 pi r delta Z, that is nothing but the volume of the cylindrical element, into pi V is a volumetric rate of heat generation. So this total becomes the rate of heat generation in the element. And also the accumulation term in this case is going to be dou by dou T 2 pi r delta Z rho CPT. Okay. So here you can see rho is going to be kg per meter cube, and so that is basically mass per unit volume. This volume is multiplied here. So 2 pi r delta z is the volume. So that volume term get cancelled out. So this becomes mass. So mass into CPT is going to give me the enthalpy, and dou by dou t of that is going to give me how much heat is accumulated in the system. So clearly dou by dou t 2 pi r delta z rho CPT is going to give me what is the accumulation of heat inside this cylindrical element. So again, in this case, we can make a heat balance as what we have done in earlier case. So we can make the heat balance here. So input terms are again from the radial direction, the input term is 2 pi r delta z into qr at r. Similarly, the input from the axial direction is going to be 2 pi r delta r qz at z. The output from the radial direction is going to be 2 pi r 2 pi r delta z into qr r plus delta r. And similarly, the output from the axial direction is going to be 2 pi r delta r qz at z plus delta z. And finally, we will have a accumulation generation term, and that is going to be volume into rho uh, volume into the volumetric rate of generation, so that becomes 2 pi r delta z into psi v. This is nothing but the generation term, and this entire thing should be equal to dou by dou t 2 pi r delta z rho cpt out. And again we can divide this entire equation by 2 pi r delta z. So by dividing this entire equation by 2, we can divide this entire equation by 2 pi delta z. R will not be there here. Okay, this R will not be there. So by doing that, what we get is because since this R is varying here, so we cannot divide it by R. So this R, the R term should not be there here. Okay. Okay, I will correct it. So by rearranging the term, what we get is RQR at R minus RQR at R plus delta R plus RQZ at Z minus RQZ at Z plus delta Z and divided by, we are going to have delta Z, and then we are going to have R psi V plus R psi V, and that is equals to R rho Cp dou t by dou t. So the can be represented using the differential equations. Since delta R and delta Z are tends to 0, so by doing that, what we get is minus dou by dou R RQR minus dou by dou Z RQZ plus R psi V equals to rho Cp R rho Cp dou t. So this is equation number 1. Equation number, if you compare equation number 1 with the plane surface what we have seen earlier, the only difference here is the R term is also there.
Sir, your voice is lagging too much.
My voice is lagging too much. Okay. Bad network quality. Let me just switch to some other network. Is it clear now? Voice?
Yes,
Hello.
sir.
So in between, this internet connectivity is messing up. Okay. 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 So from the heat balance for the rectangular surface as shown at the top, we can rearrange the term and what we get finally is the equation number 1 where we are getting minus dou by dou r r q r minus dou by dou z r q z plus r psi v equals to r rho cp dou t by dt. Here the only difference if you look at with respect to the planar geometry is here you are getting rqr term inside the difference. Similar to what we have done earlier, we can put this heat flux from the Fourier law of heat conduction. So heat flux QR can be obtained as minus K dou T by dou R, and similarly QZ can be obtained as minus K dou T by dou Z. And if you put equation number 2 in equation number 1, what we get is K dou T K dou by dou R dou T by dou R plus KR dou square T by dou Z square. So here we are assuming that the thermal conductivity is not varying along the radial direction independent of the temperature, and therefore we can take it out from the differential. So K is taken out in both the cases. And so therefore what we get is K dou by dou R dou T by dou R plus KR dou square T by dou Z square plus R in the dou by dou Z R Q Z. Here R we can take it out from the differential because this is this entire term is varying with respect to Z and it is independent. So R is not function of Z here. So R we put here. So that is taken out here in this the final expression here. You can see the R is taken out from the differential. So this becomes KR dou square T by dou Z square by putting the Fourier law of heat conduction. So this entire thing is equals to R rho Cp dou T by dou T, and this we can again simplify in terms of the thermal diffusivity. So K by rho Cp is the thermal diffusivity. If we rearrange the term, what we get is 1 by alpha dou T by dou T equals to 1 by R dou by dou R in the bracket R dou T by dou R plus dou square T by dou Z square plus IV by K. So this is the final obtained. Again, equation little to dou square T by dou R square plus 1 by R dou T by dou R plus dou square T by dou Z square plus IV by K. If you compare this equation with what the equation which we have obtained, the middle term 1 by additional in when we are looking at this is the additional term coming in. Otherwise, this is nearly the same. If you can go back and see, if you compare this equation, you can see this K we can take it here. So IV by K. So this becomes here. You can see this equation is dou square T by dou x square plus dou square T square plus dou square T by dou Z square plus psi V by K equals 1 by alpha dou T by dou T. And if you compare this equation with the equation which we have obtained for the cylindrical geometry, this additional term 1 by R to R additional term is there in the cylindrical geometry. That's it. Other than that, this equation is nearly the same. Is it clear to everyone?
Sir, why there should be a R with QZ in equation 1?
Okay. Let us
If we
go
will
back.
divide by the volume of the control volume, then in case of Z, it should cancel out. Because
we are not dividing by the volume here. We are not dividing by volume here. Divide by 2, that's it. R will not be divided. R will not be divided because here you can see in the first equation this R in the first term this R is function here, isn't it? In the second case if you look at this particular form here, R we can take it out. But other than that, here we cannot take it. We cannot
But
take
sir,
R
in
out of this
shell
equation.
balances, we divide by the volume of control volume.
Who said?
Sir, in transfer phenomena, we have been
In the
doing
head,
this.
whatever the common. No. We are dividing by a common term. Okay. For example, here the common term, if you look at the previous case, the common term is delta x, delta y, delta z. That is why we have divided. This is the common term here. So this delta x will be in the denominator in the first, in the second delta y you will have, in the third you will have delta z, something like that. Okay. Even if you divide, let's say, okay, let us go back, go with whatever convention you are saying. Let us divide by volume. Then what will happen? This R will not get cancelled out.
The first
Even
term
if
is
you
okay.
divide.
I understand that for QR, it is not at same R. First it is at R and then it R by delta R. But in terms of QZ,
But still,
it is not
in
in
the
R.
first equation itself, you will have a R in the denominator, R dr. Then the differentiation cannot be written in a different. You
So, but
require.
we can then multiply
Then
that
you have
R
to
with the
multiply.
whole equation.
Yes, then you have to multiply. Yes, that is what I'm saying.
The same
Then you will
equation
have
will
to
come.
multiply by R. Correct. So ultimately we are getting the same thing, isn't it? This R will come out here.
Okay, that will be outside. I got it.
Anyway, this R will come out in the equation 1. Okay. Is it okay? Can
Yes,
we
sir.
go
Yes,
ahead?
sir. Yes.
Okay. Okay. So now let's look at the last case of the spherical solid. Again, I am not giving more detail. I'm directly making the heat balance because now it is becoming monotonous and nearly the same, isn't it? So the heat input to the shell in the spherical geometry is going to be what? The surface area 4 pi r square into the heat flux QR at R. That is going to be the heat input to the shell in the very phase. What will be the from the shell? 4 pi r square into QR at R plus delta R. Correct. Again, in case of spherical case, the heat input and heat output only will take place in a radial direction. There is no axial direction there, isn't it? So only one input term, one output term is going to be there. Unlike in the cylindrical case, we had 2 input and 2 output term. In a planar case, we had 3 input and 3 output term, isn't it? Plus the generation term is going to be again the volume into volumetric rate of heat generation psi v. So 4 pi r square delta R, that is going to be the volume into psi v. And this entire thing will be equals to the accumulation term. So that becomes rho by rho t, again volume into density into Cp into T, isn't it? So if you divide again by 4 pi r square delta R entire, and then we will get a difference equation for this R square QR at R square QR at R plus delta R divided by delta R is going to be there. So that will be represented as dou by dou R square QR. Okay, and again there will be a R square psi v term will be there. So here again we are going to divide 4 pi delta R, not by 4 pi R square delta R. Okay. Even if you divide, you have to multiply it by R square later on, because R square term will be there in the denominator. To get rid of that R square term, you have to multiply by R square. So anyway, this again I'm going to correct. Let me just check. Can I make changes? No. Okay. Okay. So by rearranging the term, what we get is the equation number 1. So equation number 1, we are going to get again here minus sign is going because we are going to get the difference equation as QR at R minus R square QR at R minus R square QR at R plus delta. Remember the differential equation you require R square QR at R plus delta R minus QR R square QR at R should be there, isn't it? Divided by delta. So that minus sign is coming because the output term is coming minus, isn't it? So that minus sign is coming here to make this output term plus and the input term as negative. Okay. The generation term, again, from the generation term, what we are going to have is r square psi v, r square psi v, and this entire thing should be equals to r square rho cp dot t by dot t. So again, if you compare all three equations from planar geometry to cylindrical geometry and to spherical geometry, now you will see that this r square term was not there at all in a planar cylindrical geometry with qr, and in a spherical geometry we are having r square qr. Okay. Again, from the Fourier law of heat conduction, QR is obtained as minus K dot T by dou R, and we can put it here in place of QR in equation number 1. And by doing that, what we get is K dou by dou R, R square dot T by dou R plus R square psi V equals to R square rho Cp dot T by dot T. So here again K is taken out because we are assuming that it is constant and is not varying along the radial direction, as well as it is independent of temperature. Again, if we rearrange the term and represent this K by rho Cp as alpha, alpha is a thermal diffusivity. So what we get is 1 by alpha dot T by dot T equals to 1 by R square dou by dou R, R square dot T by dou R plus psi V by K. Now, if we compare this particular equation by simplifying, again, if we simplify this equation, what we get is 1 by alpha dou T by dou T, and that is equals to dou square T by dou R square plus 2 by R dou T by dou R plus psi V by K. So this is this middle term. 2 by R dou T by dou R is the additional term which we are getting if we compare with respect to the planar geometry. Even in the cylindrical geometry also we are getting 1 by R dou T by dou R term. Okay. So these are the generalized equations. These are the generalized equations. These are the most generalized equation. Here you can see we have not only assumed that there is a heat generation. We have assumed the accumulation. We have also assumed the heat transfer from all the directions. So here you can see spherical case there is only radial direction is present. Here in rectangular case we had radial as well as axial direction, and in case of planar geometry we have also considered x, y and z, all three directions. We have assumed there is a heat generation is also there, accumulation term is also there. So these are the most generalized expressions. The simplifications which we have assumed here is the thermal conductivity we have assumed constant. Thermal conductivity we have assumed that is not varying with respect to the direction. Also Cp and rho we have assumed that these are independent of the temperature. So these are the assumptions we have used. Other than that, these three equations which we have obtained for planar, cylindrical and spherical geometry, these are the generalized expressions. These are the generalized expressions. Okay. So is it clear to everyone?
Sir, on the previous page, why was there a 2 in the numerator? Or rather in this page itself?
Why there is a differentiate? These are the simplification, isn't it? You just differentiate r square. What you are going to get?
Fair. Got it. Sorry. Fine.
Okay. Okay. Now, so far we have, started with the simple, heat conduction. Then we started with the planar surface with no complications at all. Then we moved to the curved surfaces like spherical and cylindrical. After that, we have added generation term. Then we have added accumulation term. Now let's move one step further. Okay. So what will be the one step further? Now let's look at the transient heat flow in a semi-infinite solid. So that means so far we were looking at the solid or whatever the system we were looking at was finite in the thickness. Okay, now let us look at a semi-infinite solid. So what I mean by semi-infinite solid is if you look at this slab along the x direction, the thickness is infinite. That is what it is. Okay, along the x direction, the thickness is infinite. So how the heat is uh, uh, heat, heat will be transferred in such cases that we are going to look at. Okay, this is one more step ahead than what we have seen so far. So consider the semi-infinite solids shown in the figure, maintained at some initial temperature Ti. So the temperature of the solid initially is Ti. The surface temperature is suddenly lowered and maintained at a temperature T0. Suddenly the temperature of the surface is lowered to a temperature T0. What we are interested in finding out is how the temperature is going to be distributed as a function of time. Okay, so here the flux at this surface will be given as Q0, which is nothing but minus Ka dou T by dou x at x equals to 0. Again, we are only looking at the heat transfer along the x direction. We are not looking at the heat transfer along the z direction or a y direction, and therefore the equation which we have derived earlier for the planar geometry, if you can go back, this particular equation we can simplify. Remember, I said at that time this is a generalized expression. So we can simplify this generalized expression for a one-dimensional heat conduction. So that can be given as equation number 1. So equation number 1 is nothing but dou square T by dou x square should be equals to 1 by alpha dou square T by dou T. This is also called as Fourier second law. Or sometimes these are also this equation is also referred as Fourier second law. Okay. Now, the derivation of this temperature distribution also I have given on the right hand side here, but we will not go in that detail. But let me just give you the final expression first, so that we will appreciate what is important here, and then probably we will browse through the derivation. We will not go in the detail of this derivation. Okay. Okay, so we start with equation number 1, dou square T by dou x square equals to 1 by alpha dou T by dou T. And what are the boundary conditions here? The boundary conditions is at T x 0 should be Ti. So that means what? At any x when time T is equals to 0, the temperature is Ti. So that is what we are having, isn't it? The temperature of this slab is going to be Ti. Time T equals to 0 at any x. The another boundary condition is T 0 T equals to T0. So that means what? When x is 0, that means at this bound at any time T, the temperature is T0. So these are the two boundary conditions. If you solve these particular equations, the solution of this equation is obtained as Txt. Txt is nothing but the temperature at any location x and any time t minus T0 divided by Ti minus T0, and that is given as error function x by 2 under root alpha t, where alpha is nothing but the diffusivity. So the solution of this equation, analytical solution of this equation is not possible. The solution of this equation is represented in the form of error function, and the value of the error function is given normally given in a tabulated form, and based on this value of the error function you can calculate. So analytical expression is not possible for this. Okay. And the error function is defined as error function x by 2 alpha t is defined as, or error function z can be defined as 2 by under root pi integral 0 to z. In this case it is x by 2 under root alpha t and e raised to the power minus eta square dn, where eta is some dummy variable. Okay. Clear? So this is how the final temperature distribution can be represented for the case when there is a semi-infinite solid. I have also given a derivation. So here first the variables are represented in a dimensionless form. Here you can see the theta is represented as t minus t naught. So this equation 1 can be represented in terms of theta as dou square theta divided by dou x square equals to 1 by alpha dou theta by dou t, and that is equation number 2. Again, based on this initial boundary conditions, the boundary conditions in terms of theta are also given here. So at t equals to 0, time t equals to 0 for all x, theta is given as t minus t naught. So that becomes theta naught. Similarly, at x equals to 0, for all t greater than 0, theta becomes t naught minus t naught, that becomes 0. And similarly, at x equals to infinity, at the distance x equals to infinity from the left hand side wall, what we get is theta equals to t minus t naught, so that becomes theta naught. Okay, so that is what the definition of the semi-infinite solid. So the temperature distribution will not, the temperature profile is going to become a flat to the actual temperature T. So that becomes theta equals to T minus T naught is equals to theta naught here. Okay. Okay. Again,
Sir, could you please explain this topic? This is not getting into our head well.
Okay.
This is
okay. So far what we were looking at is the solid slab or cylindrical surface. We used to take the thickness. If you can go back and see here, this thickness is finite, isn't it? This length is L here. Here you can see here also the thickness you will see as a finite thickness, isn't it?